Yeah, so that's going to be an interesting one. So let me go to the chapter on that real quick. The main idea with the stack frame is that since we only have so many registers, we obviously can't store all of our variables in the register. So we kind of use a stack frame to kind of handle that for us. Specifically, normally what we do is when we're calling like a function, we prepare all the variables and kind of like toss them onto the stack. And then once we kind of enter that function, it will kind of pop things off the stack. So I guess my question is, what specifics questions do you have about the stack?
So one thing, I was working on the homework last night, and one thing that was kind of confusing me was the way you, how would I say this? Once you move like a value or something onto the stack, how do you like get back to it? How would you access that variable that you've put onto the stack frame?
Yeah, so I like to think of the stack frame as sort of an array almost. So what you would do is what you might have noticed in either just playing around this by yourself or just looking at like some of the stuff in the book is that whenever you start the stack frame, I shouldn't say start, but whenever you are about to store variables in the stack frame, do you notice that like subtraction operation?
Right, yeah.
That's essentially allocating enough room. So let's say I want to go ahead and put two integers onto the stack. So what I would do is I would subtract 8 from it, and as a result, I kind of like have 8 bytes freed up, and then I would go. You would have to do that weird negative thing because the stack pointer is pointing at the front of the stack. So you would have to jump back 8. You would read the next 4 bytes, and that would basically be the first variable that you placed in. And then if you read the next 4 bytes afterwards, that would get your second variable out. So if you kind of like contrast this as an array, the same idea kind of persists with the array. You allocate that room of, say, an array of 2 integers. So you would allocate 8 bytes, and then you would jump to the beginning, read the next 4 bytes, and then at that position, you would then read the next 4 bytes to get your next integer.
Is there some kind of like weird thing that happens with the offsets when you're accessing something there? Because what I noticed in one of the problems, and I could have just been bad at reading the assembly code, but something that confused me was it seemed like they put like one of the variables onto the stack frame by just moving it onto like the dereferenced or like, you know, RSP in parentheses. But then when it wanted to access that variable later, instead of just accessing that address, it like offset it by 4. Or like it wanted to do that.
Can you go ahead and point me to the page you're looking at?
Yeah, let me pull it up. It was the first problem, I believe, which was I think 3.66 maybe. Let me just double check. Yeah, 3.66. Oh, but you know what? It wasn't that one. It was the second one. It was 3.67.
Okay.
And it looks like it allocates 104 bytes. And then in eval, it puts X, which is an RDI, onto the stack frame at the address of RSP. But later in process, when it wants to access that, it seems like it's going 8 up. Or yeah, not 4, but 8 up instead of just accessing at RSP.
Let's see. So I just want to make sure I got the question right. Your question would be that on the process on line 3, why it's doing the 24 parentheses RSP?
No, I understand that one because that's for Z, I think. But the thing that's confusing me is for well, we could just do it just with X, for example. So X is an RDI in eval, puts it onto the stack frame at the address that RSP is. And then in process, it should have to access X again at some point, because just reading the C code, that's what should happen. But it never actually dereferences RSP directly. It only goes 8 up and then 16 up and then 24 up. It's all offset by 8 from what it does in the in eval, if that makes sense, I guess.
Yeah, let me go ahead and read it for a moment. And anyone who also has a comment, feel free to chime in on this. I'm hoping that this can be a little more, discussion based. But let me read this.
Is there like a list of topics that the exam's going to cover anywhere, or?
As far as the first 3 chapters, beyond that, not really. I believe Meehan should have said first 3 chapters, and I think the assignment was publish, and I think you guys can click on it. But correct me if I'm wrong. What I'm reading here is that it'll be 54 questions ranging from 1 to 4 points each, and you're given about roughly 2 minutes per question. So my understanding of what's happening in an eval is that it's getting ready to call a process, but to do so, it's going to have to put all the variables onto the stack frame. So line 5 through 7 are each adding X, Y, and Z to the stack frame,
right,
prior to calling the process.
Yeah, and that part makes sense to me. But the thing that doesn't make sense to me is the fact that in process, it never actually accesses that address at the top of the stack pointer. So that's where it threw X, right? Which is just at the top of the stack pointer. But by reading the process C code, it seems like X should be in the second element of the U array in R, but it never actually accesses that in process.
So it's kind of a weird situation with what eval does, because it makes a string, and it kind of creates it using X and Y, and it kind of then points to another string. It's kind of an interesting use of a struct.
A string?
Yeah, because you can see it's calling it string A because it kind of defined that as a struct on the beginning of 3.67.
I think it's just str for struct, because unless I'm misinterpreting it.
No, you probably got it right.
I don't see any strings in here.
Sorry, when I read str, I immediately think string. So yeah, it's a struct A, which is defined using 2 long variables. So let's see what it does. It goes to eval. It's raw process. It reads off the next 24, A1624 onto RDX. Yeah, it's kind of treating it as like one continuous string. So now that it's in a struct, it's not really treating it as it's not treating it as like X and Y anymore. It's treating it as a struct. So when we look at process, it's only given the struct A as S. And so when it needs to access, say, SA1 or SA of 0, it offsets, it treats it essentially as an array.
Yeah, no, I get that.
The values from it.
I get that much, but what I guess my main confusion here is that in process, it accesses SA0, which in this case should be X.
Mm-hmm.
But when I look at the assembly code for process, it never accesses where that would be on the stack pointer, which would just be the base of the stack pointer, because that's where it starts SA at the beginning, then the first element would just be at the beginning, but then in process it never seems to access that. It starts by going 8 up from it. So I was the thing I was thinking about is maybe when you're accessing it, does it like read backwards or something? Do you like pass it the reference or the address to the end of the value or something?
Let's see. I want to say that my intuition right now is the reason why you're not seeing it directly be at like RSP is because I believe the previous address that it was called from is pushed on top of the stack. But let me verify that. Because we need to, the stack needs to, not the stack, but the code needs to figure out some way to travel back.
Yeah.
And I believe that's added to the top of the stack. So I think you would see an offset of 8 on 64-bit. But let me make sure. Does that sound right to everyone else?
Is that because it has to put the return address on there when it calls?
Yeah.
Gotcha. Okay.
But it might. I want to make sure I verify that before I tell you that is the correct answer. Does anyone else have comments towards that? Does that sound right to someone? Does that sound wrong? Or are people equally confused? Any kind of feedback?
I wish that Meehan had made a fucking study guide.
Yeah, that would be nice.
I think what you was right. So just like when the call instruction is invoked, it just automatically will push the like return address for after the call onto the stack. Is that the type of thing that happens?
I want to say it is. And
okay.
When we're looking through the chapters, it might refer to ESP, but that's because it's on like 32-bit.
Gotcha. I mean, I'm going to assume that is the case because if it is, it makes everything make sense, I think.
It might store it ahead. That's the thing that's caused confusing too, because the stack pointer, it doesn't necessarily have to point to the top of the stack. It makes a lot of sense for it to point to the top of the stack, but a stack can kind of point anywhere. Have you guys been talking about structs recently?
Yeah, yesterday and today we talked about them in lecture.
Did he say that's a part of chapter 3?
I think he said it would be on the exam, but I don't know if he said it was. Yeah, I think it's part of chapter 3 because these homework problems are from chapter 3.
Okay, let me look at that further. Oh yeah, yes, they are 3.9. Yeah, he said up to chapter 3 would be on there. Interesting. Okay, give me one bit. Do you know where the chapter is on stacks?
I don't know. I don't remember exactly where it was.
Okay. You see that structs and unions are 3.9. Two 2.6, 2.7. Okay. Okay, let's look at that homework problem again. 3.67. Right? No, it wasn't 3.67. Which one was it?
Yeah, 067. That was right.
Oh. Okay. I had the wrong book PDF. Found it. No, it's not cheating to share notes. It's what falls under cheating would be like anything of like, here's how I did the homework solution or project. Like if there's a homework problem, like let's say a homework problem number 5, if there's a problem in the book that is not one of our homeworks, you could write up the answer with it and share it with someone. That would be fine because that's not being something that's graded for this course. It's anything that's graded for this course that if you share it would be considered cheating. Essentially, if you're sharing something that you will be graded on, then it's cheating.
Is it only with the other students? Like, are we allowed to share it with the tutors?
With what?
With the tutors.
Like the CS mentors?
Yeah.
No, it should be fine. And they should also be trained to like know that if you're giving them too much information or whatnot. So they'll if they think something's up, they'll stop you and let you know, hopefully. Okay, let me look at this eval thing again. That's going to be my guess. My guess is that the stack is implicitly adding the address. And in this case, I think it's going to be 64-bit. So it makes sense that it's always at an offset of 8.
Yeah, after you mentioned that, everything like makes more sense because I was a little bit confused also about the second line in the fourth line in process where it has to dereference RDX because I thought that 24 from the RSP was just literally Z. But if it gets offset by 8, it makes sense why that would be a reference to Z and it has to dereference it. So that explanation makes sense to me.
And I think RDX, if we look at the type of register RDX, that will also give us some answers. Because there is a register that I remember that that will basically return will have the return address. Yeah, anything that was to start as a pointer. And it's important to note that pointers are going to be the same size for anything. So a character pointer on a 32-bit system is just as big as an integer pointer. There's no difference between the two.
So just slightly related question, would return also implicitly pop off the return address?
Yes, it should.
Okay.
Pretty sure RDX is the one used to return, but now I'm not sure anymore.
I think it's RAX is the return
RAX. Okay. Now I want to point out that on the syllabus it says that these exams are open book, so I would encourage you all to kind of like, don't beat into your mind like what all the different bite sizes are, because there is a nice table in the book that just shows you that. So I would encourage you all to kind of like go through the book and find those tables and useful pages that you want to look at quickly and just bookmark them and not like waste time during the exam to flip there. I'm not making a recording of this, but if anyone would like to make a recording of it and post it somewhere, that would be fine. I'm not sure. I would ask Meehan about that. My information I'm giving out is purely based off the syllabus and the description of the exam. Okay, let's see. So you asked a question about load effective address. What is that referring to exactly? What part? Just kind of like the assembly. Um, Let me refresh myself real quick. I didn't expect this many assembly codes, to be honest. Questions.
Is the exam multiple choice or short answer or a mix?
I believe most of them is going to be multiple choice. If I recall, a lot of the questions are going to be like, look at the following C code. Which of the following options best represent the assembly code that would be outputted by like line 6, and vice versa? Or look at the following binary. Which of the values listed below represents the integer representation of that binary?
Oh, perfect.
Which terms are you confused on? Okay. So load effective address is going to basically, when we do a move, I don't know what to call it, instruction on assembly, that's like saying, hey, go ahead and move to get the information available at this address, and not just the address itself, but the actual content itself, and load that into some register. Where load effective address is going to kind of omit that last step, where it won't get that information there. It will instead just keep it as an address. So it loads the effective address of it. So consider this like an array, say some array of A. If I do A sub 1, that's going to go into memory where A is a pointer. It's going to jump ahead some number of bytes to go to the first element in A. It will load it up and return the result. Where load effective address will instead be the pointer at A plus some number of bytes. So how it would translate into C code, it would be something along the lines of the address of A, and you basically, if you do A sub 0, that would be like move. Sorry, if you do A sub 1, that would effectively be like a move operation. And if you do A plus say 4 bytes for an integer array, that would effectively get you the address that the second element of A is located in. So it's the difference between saying, hey, go to this memory address and load the information there versus just offset my memory address. The foundational stuff, you need to be very confident in reading binary. If you can probably definitely expect questions that will say, look at this binary, tell me what the value is, tell me what the float value is, and vice versa. Given the float, say 3.5, write out what the binary is. You need to remember all your basic Boolean algebra operations, and you also need to make sure you know the difference between those and the logical operations, that is the logical and the logical not. You need to be confident with masking. That is, if they tell you to get the most significant byte or least significant byte, those type of questions, you should be able to answer that. You do need to know the IEEE rules because they're going to be most important to floats. I don't know what you mean by if the excuse me. I don't know what you mean by if it's the values will change. Oh, well, I would say IEEE is not directly countering the values we use. Like the IEEE standards are still the same for 32 bits versus say 64 bits. It has set rules defined for like single precision and double precision, but they're not like separate from each other. Does that make sense? Like regardless of the number of bits used, it's still an IEEE standard to round to the nearest even. Do you know what I'm kind of trying to say there? The number of bits used isn't really specific to IEEE. IEEE kind of just sets the standard notation for everything, like regardless of the number of bits, these are the rules that we want to use. Like the IEEE will still be a thing even if we go up to something crazy like 128 bits. Do you know if there are any questions? I do not recall. From what I remember, it was pretty much multiple choice. I think Professor Meehan liked the exams to be easily graded. So I think he makes them multiple choice for the most part. If I remember correctly from when I took the course with him, a lot of it was just multiple choice. Some of them might be like fill in the box, but like it'll still be like an answer. But don't take that as a guaranteed, because he could have changed it for all I know. Yeah, and we can talk about the bomb lab more. I kind of, unless everyone wants to talk about it, I kind of wanted to not talk about the bomb lab today, just so we can focus on the exam. But if you had questions about the bomb lab, feel free to email me if I'm your TA or email your other TA. The bomb lab is really kind of just like putting everything to practice. But is there any specific, let's just go down the chapters and see how people feel about that. So let me pull that up on my end. So chapter 1 is more introductory than anything. Okay, how do you guys feel about integers? Any questions about integers at all? The only dumb question is the question not asked. Or maybe there's more dumb questions, I don't know. Just ask me a question about integers. I'll give this an awkward pause for a minute before I move on. Cool. So definitely remember your 2's complement. That's going to be important. Let's move on to floats. So how does everyone feel about floats? And I want to mention about the integer is you should also feel confident about switching between any of the base systems. So understand that binary is base 2, decimal is base 10, hex is base 16, and also understand how to translate a number to any base. So if I say translate your number to base 7, you should be able to do so. Does everyone feel comfortable about the idea of translating to a base, an arbitrary base?
Not really. Is there like a standard sort of procedure for translating to any base or something?
Yeah, and
Because I sort of know like how to do, how to do binary to hexadecimal, to decimal, all that, but I don't really know, I don't know the generalized version of that.
mm-hmm. So really it just has to do with kind of like how it, oh no, my tablet died. Oh, it'll turn on. For now, I'll just use my mouse. So really, if I just have like these, this is just going to be binary. So we know that this represents 2 to the 1, and this kind of represents 2 to the 0. And the number here really kind of represents how many of those are we going to add. And so in binary, of course, if this is a 1, that means we're going to add 1 to the 0. And this is a 0, that means we're adding none of 2 to the 1. So our final result is 2 to the 0. So that's kind of like basic binary, of course. And when we think about decimal, just like in the normal number system, it kind of works the same way. If I have 17, this is effectively saying add 7 ones. And this is effectively saying add 1 10. So it kind of still follows the same pattern. And so if I have this new system that's going to be base 4, let's actually choose a different number. Let's do base 5. Then effectively, if I have 2 positions saved for it, I can do anything as big as small as 0, 0, or anything as big as 4, 4. And effectively, what this is saying is that this position here is how many 5 to the 0s we add, and this is effectively saying how many 5 to the 1s we add. So if I just come up with a random number, say 2, 3, this is effectively saying I should add 3 5 to the 0s, which is of course 1, and I should add 2 5 to the 1s, resulting in an answer of 13. And so this would be in the base 5 system. And so using this system, I can make as big of a number as 29 with just 2 locations here. The way I'm getting 29 is, it shouldn't be 29. It would be 4 times 5, so 20, and then 4 times 5 to the 0, so 24. I was off by 1. And you can kind of see a pattern with this and the other ones, because if I do 5 squared, specifically squared because that's the number of spots I have reserved for it, minus 1, I'll get 24. And so if I add another number, the maximum I can produce is 124, and so on. So using this system is kind of how you're going to convert between them all.
Let's say it had the opposite problem. So it was like, here's 23. Now write that, like 23 in decimal, now write that in base 5.
Okay, yeah. So the question I would then ask is, I can use 5 to the 2, 5 to the 1, and 5 to the 0. And so 5 to the 2 is 25. So I ask myself, how many 25s can I fit into this number? And the answer is, well, 0. And the next question I asked myself is, how many 5 to the 1s can I fit in this number? And the answer would be 4. And lastly, the question would be, how many 5 to the 0s can I fit in this number? Well, I should say after we subtract it. So 23 minus 20 is 3. And then the answer would be, well, that's a butchered 3. That would be 3. So this would be represented as 23 in base 5. And we can kind of go back and check our math. This is suggesting that we add 4 of 5 to the 1s So that's going to be 20. And this is suggesting we add 3 of 5 to the 0. And that would be 3. So we get the answer 23. And it's kind of the same when we kind of go to binary, because if I'm trying to write 9, the question I ask myself is, how many 8s can I fit in there? And then how many 4s? And then how many 2s? And then how many 1s? Or in other words, how many 2 to the 3s? How many 2 to the 2s? How many 2 to the 1s? And how many 2 to the 0s? And so that would be 0, 1, 8. And then we would subtract 8 from it. So that'd be 9 minus 8, which is 1. And we'll get that number in base 2. So that's going to be kind of the generalized rule from switching to any kind of base systems.
Got you. And then once you go past the decimal point, would you just be doing the same thing? Like, say it was, base 5, it'd be 5. How many 5 to the -1s can I fit in here? How many 5 to the -2s can I fit in here?
So if this is like a float representation, and then we have like 0, 1, this is effectively saying 1/2. This is effectively saying 1/4, and so on. So it would be the same idea, except if it was like, say, base 3, it would be either 0, 1, or 2. And this would effectively mean 0 thirds, 1/3, or 2/3. And then it will continue on from there. Then it will be 0 over 3 squared, 1 over 3 squared, 2 over 3 squared, and etc. So it will still follow the same system.
Awesome.
Just like you consider with binary, the fact that we go by 0.1s is because it's 1 over 10, 2 over 10, 3 over 10, and so on, up till 9 over 10. Let me stop that, and let's look at the chapter some more. So that's going to be translating between the base systems. How are you guys feel about the normalized, unnormalized, sorry, I should say denormalized and special values of floats?
A little bit more fuzzy, but generally pretty solid.
Yeah, we can go over it. Let me get my nice whiteboard back up. Let me also try to figure out why my tablet won't connect. Oh, cool, it works. Okay, so we're gonna have 3 different situations. We're gonna have our normalized case. I'll write this with norm. We're gonna have our denormalized case, and we're gonna have our special case. So our special case is gonna consist of either plus or minus affinity. Let me draw that better. Nope, still a mistake. Or it's gonna produce nan. The denormalized case is specifically for very small values, and the normalized case is not necessarily not small values, but just larger values. And so the main rationale for having the denormalized case is that once we get down to these smaller numbers, we, just as people or scientists, however you want to describe us, want to have a good representation of very tiny numbers. If we kind of continued on with just using, if we didn't have the denormalized case, it would still work out, but we just wouldn't be able to get as small as numbers that we would hope. So let me reference something in the book real quick. Yeah. So the special case, maybe I write this in a different color. The special case is going to have the situation where our exponent is just going to consist of a bunch of 1s. And that's how we immediately know we're in a special case. So if you see a problem and you see a bunch of 1s in the exponent, just think to yourself, special case. Otherwise, if we're in the denormalized case, we see a bunch of zeros. Otherwise, if we're in the normalized case, E just won't be all zeros and it won't be all ones. It'll be somewhere in the in-between. And here's going to be my question. What's going to be the main difference, ignoring the E being all zeros or ones? What's going to be the main difference that we do in the denormalized case versus normalized case? Anyone have an idea of what we'd do differently? Yeah. So that's pretty much it's only going to be the main difference. Either we add 1 to the M value, which is not going to be mantissa. They call it the significant. Or just want to have 1 in the denormalized case. So otherwise, they're pretty much treated the same. And from this, we can kind of like easily, I would imagine you'll probably have some questions being like, what is the largest denormalized value that we can have? Would you guys be able to answer that? So for, let me get rid of that. I want a black pen again. So this is going to be our sign bit. That's going to be our E. And then the question is kind of how F it looks. Yeah, it will be all ones. And the reasoning for that is that this is effectively saying 1/2, 1/4, and so on. And so this kind of gets us a value that's F is not going to be quite this, but it will be close to saying 0.9999. We won't be able to represent it exactly due to the nature of binary, but that would effectively be what it looks like. And likewise, the smallest number that we can represent in the denormalized case without being 0 is going to look like this. Or I should say 0, then 1. Because that's effectively adding like 1 over to the, I want to say it's 23. Is there any lingering questions on the normalized, denormalized case? The adding 1 thing. Yeah, so that idea is that if we're in the normalized case, then, and let me go ahead and get a green pen for this. If we're in the normalized case, then effectively M is going to be equal to 1 plus F. Whereas if we're in the denormalized case, M is effectively just equal to F. So in the normalized case, we add that implicit 1, where in the denormalized case, we no longer add that implicit 1. And for all intents and purposes, that's like the main difference between normalized and denormalized case. So the main thing just to remember for the exam is that if you're ever being told to like come up with the largest float you can represent, don't fall for the trap of making it all ones, because that's going to put us in the special case. Unless the question said to do affinity, but ignoring affinity, the largest float we could represent that is not affinity would have the exponent values of 0. Wait, give myself real quick. 1, 1, ... What happens in signed versus unsigned values? Okay, yeah, that's a good question. So when you change between them, so that's going to be the interesting thing. So it's very important that you guys know the difference between casting and just saying something is something. I know that sounded weird when I said it, but what I mean is if I have x, which is a float, and I'll just do it like that. And I say that's like 1.0. If I then say that int y is equal to the casting of x, then y is effectively equal to 1. Like, we don't get any type of weirdness that occurs here. The weirdness that will occur is if we just looked at the binary of x and just said, whatever that binary is, we are now going to be treating it like an integer. So generally, so it's going to be a two-part question. Generally, when you cast between values, the compiler, and I shouldn't even say the compiler, I'll just say the machine. The machine will do its best to translate those values. And you're going to get some weirdness because you can't translate the value 1.5 as a float to an integer because there's going to be that issue of losing the decimals, essentially. But then you're also going to get the weirdness of not when you cast them, but when you just suddenly say x is unsigned. Because effectively what's happening is I'm going to pretend that we're dealing with a system that's only 1 byte long. And so this, if I'm only dealing, I shouldn't even say 1 byte, sorry, 4 bits long. When we're dealing with an integer, this is the smallest representation. And the main reasoning for this is that we will still kind of keep up the idea where this is 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. The difference is that when we're treating this as a signed value, then effectively this is being treated as like sort of a negative. And so this would be negative 2 to the 3 plus nothing else because I didn't put ones there. So this will show that the smallest value I can store is negative 2 to 3. When we're in a unsigned representation, and I'll kind of put an S up here to denote that. When we're in unsigned, this, it's still basically the same system, but this is equal to 2 to the 3 instead. So the main difference is that in the signed representation, this is being treated as the first bit is being treated as a negative offset, where in the unsigned representation, this is being treated as a just as normal. So the main idea to take away from this is that in the unsigned representation, we can store a good range of values from 0 to some amount n. And when we go to the signed representation, we basically say, okay, well, enough of this. Let's actually go ahead and reserve some of these values and add an offset so that we can actually store from about, there's going to be it's going to be the classic off by 1 syndrome, but I think it's going to be negative n over 2 minus 1. Something around there. So we're effectively, by going into the signed representation, we get all the values you could produce, and instead kind of like throw away half of them to reserve them for the negative representations. What happens in floating point when flipping between signed and unsigned? I don't think floating, is there an unsigned representation of floating points that you guys talked about? Yeah, I don't think that you're going to really talk about that. If there was a hypothetical situation, what you would probably do is just not have the exponent bias. Oh, sorry, no, I misspoke. You would just leave one, you would just have an extra bit to do what you want with it. Add it to the exponent, add it to the fractional component. That would be my guess for what happens if you no longer care about being signed. You would either add one more to your exponent bits or add one more to your fraction. So that's what you could do. Okay, let me just keep on moving through these chapters and see if there's anything interesting to talk about. So again, I think I already mentioned this, but the reasoning why, so when we kind of squish into this bias system, the main idea is that we if we treated the exponent as sort of a how we would treat like a normal, I'm trying to think how to describe this. The reason why we don't have a signed bit on the exponent is specifically because we treat it as like a unsigned integer, and so we can subtract the bias, which will effectively allow us to get one more value out of it. And we choose to let that value go into the negative. Specifically, we're in the range of 126 through to negative 127 in the 32-bit case, and we do so to allow us to represent smaller numbers. There's nothing that would have stopped us from instead allowing us to go from 127 to negative 126, but it's kind of accepted that we needed smaller numbers more than we needed big numbers. So yeah, make sure you guys are familiar with your notation in floats. So understand that when we talk about the exponent, that we can either be talking about like the bits, the representation after subtracting the bias, or even I'm forgetting the terminology now. The exponent is typically referring to the bits. The exponent value is usually referring to the exponent after we subtract the bias, and then we have 2 to the e, which is going to be basically the multiplicative factor of the exponent. So make sure that if you see a problem that says like what's lowercase e, that you don't add the bias. And if you see a problem that says that has a capital E, you do add the bias. And that's those terms are going to be at the top of 2.4 floating points. So are you asking why they chose to do 8 bits for exponent and 23 for the mantissa? I'm sure there is a set ratio. It wasn't necessarily arbitrary, but it was also a little bit arbitrary. That was kind of like a perfect ratio that people came up with. They decided that like there's like a trade-off. The more bits you add to the exponent, the larger of a value you can hold, and vice versa, the smaller of like an exponent, and then the mantissa kind of allows more precision. So it was sort of just a sweet balance that was decided. There isn't like a set formula, I would say you would have to remember. You would only, that would be considered a double, and I believe the chapter has some rules on that. I think they just times it. I think they added more to the mantissa. Let's see. So it's going to be 62 minus 50. I think it's 11 for the exponent and a good amount for the fractional component. I'm looking at page 104. It's on there. It looks like it's 52. So I would say somewhat arbitrary. They just kind of, they calculated, they found out the trade-off and decided what would be best. And that's the main reason. The only reason why there's 23 bits in the fractional component is because people decided that was a good amount, and that was established as an IEEE rule. Okay, well, if everyone's gonna, is everyone comfortable with floats? Any remaining questions about that? So I'll continue on to program, or chapter 3, I should say. And I would say that if you want to get a little more comfortable with using assembly, try to just write your own C programs and like output it into assembly and kind of like see if you can follow along with it. If you do that, make sure that you tell GCC that you want no optimizations. Otherwise, it might do some tricky stuff. Also, a big one, make sure you know that when you left shift, you are essentially multiplying by 2, and when you right shift, you're effectively dividing by 2. For example, I could definitely see a question where like the C code shows X being times by 2, and then it'll be like, which of the following options best resemble the assembly code of the source code? If you see one that is left shifting by 1, that is equivalent. Does that make sense? Cool. I don't think that's the flag. This is what I use for my flag. Or actually, I used the wrong chat. One second. There you go. That's the flag I use. So yeah, I would say going through these chapters, just looking at what is important is understand how an array looks like in assembly. Because effectively, as I mentioned, A is an address. Sorry, if A is an array, then A is effectively a pointer to an address. And the actual contents of A is stored at that address. So if you want to know what the second element of A is, you have to offset the pointer A by some amount and look at it. Is that clear to everyone? Any important register rules to remember? Oh boy, I don't know. Know that on a know that whenever there's an R, that's effectively the 64-bit representation. So, as in, don't think that RAX and EAX are necessarily different than each other. Just know that EAX is like the first 32 bits of RAX. So make sure you know that. Make sure, I would say on 3.4.1, that has like the operators of like offsetting an array value and like indexing in a scale index. Make sure you know those. How comfortable are you guys with comparison checks like the flags that get fired off when you do like jump conditions? Okay, and he did talk about that, right? That's not just like a random topic I'm pulling up. Cool. If he went over them briefly, then I will briefly go over them as well. So let me make sure I have the PDF up for this so I can see the flags. I really just need to make this whiteboard smaller. Okay. So we're going to have 4 flags that we're dealing with here. There's CF, which is going to be our carry flag, ZF, which is going to be our 0 flag, SF, which is going to be our sign flag, and OF, which is going to be our overflow flag. So the idea with this is that when we do a when we need to ask the question, oh, is X greater than Y or something along the lines of that, we have to do a comparison check to figure this out. And effectively, what a comparison check is going to look like is it's pretty much just going to be for two values, like S2 minus S1. Or specifically, I'll use the notation in the book, S1 minus S2. So it does this operation. So this can be effectively thinking as X minus Y, and it kind of will set these depending on what happens. So let's say I do the value 5 minus 4. The carrying flag is going to indicate whether or not we had to carry a most significant bit. And so this didn't have to happen, so we don't do it. This is effectively for like overflows. The 0 flag is if the most recent operation yielded a 0. So if this equaled a 0, this, and I'll actually go ahead and write little comments under here. So effectively, CF is equal to 0 because we did not carry anything. ZF is equal to 0 because we did not get a 0 from our most recent result. SF, this is going to return a 1 if the most recent operation is a 1. Yeah, I can elaborate over the most significant bit in a moment, and yeah, you're free to record it. This is going to be a 1 if the most recent operation yielded a negative value, and in this case, 5 minus 4 is 1, so that did not occur. And then the overflow flag is going to be if we overflowed. Oh, does it not even let you? Let me see. I don't even know what this option would be. I haven't been asked this before. I don't know if I can find it. I think I have to do it through the web, which is going to be annoying. Yeah, I don't know if I can turn that on right now. And so continue on with the example. In this case, none of the flags were set. And this kind of, if you look at the table for jump conditions, these are going to be, using these flags, we can essentially figure out what happened. So the carry flag, that's effectively when it's most important to deal with unsigned integers, but effectively it's saying that the most significant bit was carried out. So say I'm going to pretend that I'm dealing with unsigned integers that are 4 bits. If I add these two guys together, I'll get an answer like this, which isn't the true answer because there's a kind of a 1 that kind of like went off the edge and disappeared. So this is going to be when the carry flag occurs. It's specifically to unsigned integers, which is when this is most important. Did that clarify the question about the carry flag? Cool. And so using these checks, we can kind of come up with anything that we need to do. This is going to be our greater check, greater than check, because you can kind of like notice patterns in this. Because if I had the same number, my pencil back. Oh, that's not a pencil. So if I had like the same number, we can see that this becomes a 0. So this is when the 0 flag will get set off. So this would say that our carry flag is still 0, but they're all going to be pretty much 0 instead of our 0 flag. And because this is set to 1, we know that they're equal to each other. And so if you look at our jump conditions in the chapter, in the book, you can see a lot of them are going to be using these flags as a way to indicate what happened. So I wouldn't be surprised if there was a question like this. We have X greater than Y. And the question is, and it will say something like the overflow flag was 0. The 0 flag was 1. Carry flag is 0. And the sign flag was 0. And it would be like, what happened? And so in this case, we could look at the table for this, but in this case, it's very, I think it's very clear that since this kind of fired off, we know that X is actually equal to Y, which indicates that this statement is false. And so this does not run. So this kind of, these guys will give us all the hints we need to determine how X and Y compares without even knowing what X and Y was. And so as a way to kind of like look at that, you don't have to remember these off the top of your head. Just note that, just know they exist. And specifically on the second edition of the book, it's on chapter 3.61. There should be a table somewhere in there that shows, that's going to be the set conditions. And there's going to be another table later on that shows the jump conditions. So in code, what this might look like, specifically in assembly, is that you see this comparison check. And I'll kind of put squiggly lines here for now to show that it compares two numbers. Actually, namely, it would do S1, S2, and the comparison we do is then S2 minus S1. Oh, I had these backwards in the book. Same idea, but backwards. S2, S1, it will do the comparison of S1 minus S2. And then from there, it might do like a jump if less than or something. Because these, notice that the flags aren't like implicitly set. They're kind of, they're always kind of set whenever you do this comparison or test condition. So yeah, there's a comparison and there's also a test, which is effectively doing, given two numbers, doing that. And it will have the same idea where it will set those flags depending on what occurred out of those most recent operations. Let me continue on. So with the stack, make sure you know that the whole point of the stack is that we can't just store everything we want in registers. So we need to have that stack to kind of hold things for us. And then the idea is that once we jump to a new function, the function's like, okay, let me get the next value off the stack. Let me just keep on going like that. And there's an offset by 8, specifically to handle the return address. And I should mention that I'm saying 8 because I'm assuming it's 64-bit system, but just be cautious that if the question says something along the lines of assuming a 32-bit computer, what is, some question, just note that, just make sure you keep in mind the number of bits that are in the computer. Like don't be fooled by saying 8 bits on a 32-bit computer. Sorry, I should say 8 bytes for an address on a 32-bit computer. So yeah, the whole 3.6 has a lot of good stuff on jumping and conditions, which might be useful. I can definitely see a question that says like, what is, like, given the C code and this assembly code, like what is, what occurred if X is, or no, not even that. What would occur, like, given this assembly code, what would occur if X was 3 and Y was 5 or something? There's probably, from what I remember, there's a lot of questions like that, where given these conditions, what are the answers? And let me keep on going through chapter 3, see what I can find. And again, if anyone has a specific question, just say it. Just scrolling down right now to see if there's anything interesting. Oh, structs and unions. Let's talk about those a little more. I kind of talked about them a little bit in the beginning, but I want to be a little more clear on them. So what's kind of interesting is that a struct is going to group them up in like a single object, but it's still going to, its size is going to be that of the entire variables. As in, if I have a struct that contains 3 integers, then its size is 12 bytes, 4 bytes for integers. And what's kind of interesting about the union is that it's not that many. It's actually less. It's because it's gonna allocate room for the largest variable within the union, but only really have one of them at a time. Well, I guess I shouldn't say one. It'll only reserve that amount of room of the largest variable within itself. Is that clear? And I think the example that Meehan probably would have shown is some type of node system where like it either points to the left or right, and it also has a value. Does that sound familiar? Or at the very least, are people at least comfortable with the ideas of a struct versus a union? You can probably expect questions like, hey, here's this struct S1 and it's defined like so. What's going to be the number of what's going to be the size of the struct? And then also here's a union. What is going to be the size of that union? So an example of the stack with calling another function involving local variables and parameters. Yeah, so if I was calling, and let's do a code example. Let me fire up the good old terminal. Let's see. Let me go ahead and share that screen. All right. So we're going to make a test file here. And let me see if I can remember all my C syntax from the top of my head. So what I'm going to do here is I'm going to define a function func that is just going to take in the variables x, y, and z. And let's just do x, y, because I realize I already have z reserved. It's going to take in x and y, add it to some variable z, and just return z. It's kind of very straightforward. But this will kind of demonstrate what happens, I think. And so we're going to allow x to be 2. We're going to allow y to be 6. Oops. And we're going to go ahead and define z to be the result of it. And we'll go ahead and just print out z just so we can make sure everything's working. And let's go ahead and even make sure I did this right. Cool. So I am gonna use a very nasty command here that you don't necessarily need to know what it does, but it's going to compile it for me. It's also going to compile it without any optimizations and provide assembly file for that. And I'm using object dump to link the original source code with the assembly. Not very important. It's just going to give us a nice clear view of what's occurring here. So what we're going to see here is in between these lines, it's going to define, it's going to show the source code to kind of see what's happening. So here we're going to define x to be 2. So you can see that it's moving the constant 2 to our register RBP, or by offset by some amount. And then we're also going to have reserved y. So see what it does here. So this is going to be the full calling command. So this compiled for optimizations? Yes, it is. Let me think about this for a moment. It's going to be -8 and then -4, 64. You know, I actually do not feel confident enough to describe the stack pointer frame, unfortunately. I would email Meehan about that. I'd rather you guys get a good answer rather than me guessing based off my intuition. Sorry about that. I wish I could help you more there. Because the stack is such a mysterious thing. I know that doesn't instill confidence, but let me see if I can't figure out a good way. Because I will tell you that the main idea with the stack is that prior to calling the function, we're going to get all the variables that we know that the other function need and kind of add them onto the stack in order. And vice versa, the function, once we call it, is also going to pop it off vice versa to get all the variables that it needs. And the tricky part is kind of like following along that in assembly. Yeah, so I mentioned this earlier. Before you take the test, go through the chapters and, well, don't bother remembering anything that the book easily gives you as a table. So don't beat into your head like what all the sizes of the different data types are yet. You should probably know them, but for example, and then just bookmark all those sections of the book so that you can easily flip to them. You don't want to waste time during the exam trying to figure out where that page of jump conditions were when you can just easily bookmark it. As well is, since you're given the book, you might be tempted to kind of spend a long time looking for an answer to a problem. Don't do that. Instead, I would say skip the problem and continue on and kind of then go back to it. If you have additional time, then by all means, do look through the book and try to like figure out the answer, but don't waste your time doing that because it's going to be painful if you run out of time and you see that the next few questions were really quick ones that you could answer. Let me think what else. I would recommend going through the practice problems at the end of the chapters, not necessarily like rigorously solving them, but looking at each problem and then think to yourself, like, do I know how I can go about doing this problem? If the answer is yes, then kind of move on. But if you think to yourself, well, gee, I don't actually know how to do this problem, then maybe spend a little time looking into that a little more. And yeah, like Justin said, the exam's going to be 2 hours and you can take it at any point you want. So I don't know, wake up, have a cup of coffee, eat some cereal, get into the mood of things. I understand that the assembly part is going to be tricky, namely because even if I'm having a hard time kind of like thinking of the answers for you guys, it kind of shows that it's also a little kind of a odd topic. So I would probably suggest write down some C code and kind of just follow the code yourself. And let me go ahead and post this command for you guys. That's going to be, it's actually 3 commands separated by a semicolon. That is a command that you can use to compile your C code, and then it looks at the assembly of your C code, and it will have inline source comments. But yeah, it will be multiple choice. In fact, I wonder if I can even, I wonder if it lets me look at my previous exam. I don't think it will, but. And in my experience, the exams are typically going to be grade-wise a low average, but I do believe he curves in the end. So if you get like a grade that you weren't hoping to get, don't immediately beat yourself up about it. Just give it some time and see, because this class is notoriously difficult, but at the same time, they also make it a little overly difficult, in my opinion. So that's why I kind of get rounds off in the end.
Are there any resources to see like class averages or things like that for past classes?
For past classes, I can tell you what the average was on the exams, but I almost feel like that would be more demoralizing.
I mean, as long as I know it'll be curved.
I'll tell you what the average on my exam was. The final exam had an average of 75 out of 126. So I think that works out to be like 60%. No, that's 3/5. So that's going to be 60%. Wait. Yeah, I did that math right. Test 1 had an average of 29 out of 54. So that's 30 out of 54. So roughly a little higher than 60%, I think. The high was 47 out of 54. So no one got a perfect score.
And did you have Mian as well?
Yes, I did. So don't take that as this exam is going to be so hard that it kind of ruins you. Take that as in the exam is meant to be difficult, and that is also taken into account when it comes to grade, right? So take that as you will, because I've had professors in the past that like knows that the exam is going to be difficult and kind of almost expects like the highest score to be 70% or so, and then they kind of curve it afterwards. So just keep that in mind, that this exam is meant to be difficult, but he should hopefully curve depending on how the class does. I can't really speak to whether or not he will curve because I don't know. It's going to be kind of up to his discretion. Let me see if I can even look at some of the example of the questions. I'm really doubtful that it will let me. No, I can't see it. Let's see, other exam tips I can think of. Yeah, I would say that would be my main ones is to have bookmarks for all the main tables and things you need to reference. Um, if there's a question that you won't be able to answer immediately and you know you're going to have to kind of look it up in the book, I would say skip it for now and kind of move on and then use like the leftover time you have allocated to go back because you really want to get all the questions you do know done first and then tackle the ones you don't know. Um, Additionally, I believe you can probably expect, if I recall correctly, the exam is also going to be in the format where look at the C code, look at this source code for something, and then like the next 4 questions are all going to be relating to that C code. That was my experience, but again, this might be different depending on how he wants to do it. Have scratch paper available to write down notes. I would also say that sometimes use context a lot. Sometimes a question might be asking like, "What does this do?" and you may not know, but when you skip it and kind of like go on to further questions, you can kind of pick up contextual clues and be like, "Oh, this question described this register as blah, and this other question asked what that register was." If that makes sense. So sometimes just skipping ahead and like reading through the other questions kind of will refresh your mind and be like, wait, another question was asking about this too. I wonder if I can like link them up somehow. Um, um, Make sure you know that unions are only reserved to be as big as their content. I hope he doesn't do this to you guys. There was one question I had that I remember thinking, geez, well, it was I think it was like a union. It was a struct within a union within a struct or something like that. And then it was like write down what the following, write down what the values would be given these operations, and it was kind of ridiculous. So I would say maybe spend some time kind of refreshing yourself about structs and unions and like how you navigate them. The main thing I would say is just go through the practice problems, and yeah. I believe it's going to be overall curve. And yeah, I hope this helps out. I feel kind of bad for not remembering all the information about the stacks, but I do high level research. Is going to be my excuse. Any last minute lingering questions about anything? Oh boy, let's look at the homework. Sure. It's going to be, I have that PDF pulled up, I think. Load effective address to 1, RDI 4. Yeah. This, we're going to want to go back to how load effective address works. What I want to say is that this is loading up the memory. This is getting the address of RDI. The skip value is going to be 4, and we're skipping it by 1. So this is going to be adding 4 to that address. And since we're doing load effective address, that is saying, hey, the address that is at RDI, go ahead and get me the new address that is 4 bytes ahead of it, and load that into RE. Wait, you might be right. Look at the there's notation for load effective address that kind of shows the parentheses that kind of shows you what happens, and I believe that is going to be on page. Yeah, I'm not too sure now. Now I think about it either. That's going to be on one of the pages that is going to show the notation for load effective address, and that's going to be kind of like your savior. Let me find out where it is. So yeah, like this type of table that I'm describing right now, that would be a useful one to bookmark because you can see I'm trying to find it right now and it's taking me a little bit of time. Load effective address, where are you?
I can't find it right now, but there is a table. Look up that table, and it will kind of give you the information you need to know. It takes in 3 arguments, and it'll do something with those 3 arguments. And the parentheses kind of stands for like loading that up, like the contents. But then it kind of offsets when you do load effective address. It's kind of a weird situation. It kind of uses a lot of things in one go. Yeah. God, I wish I could find that table. Let me look up something real quick. Yeah, I wouldn't be able to give you the answer right now. Look through chapter 3 and go through the all the little coding samples and try to follow along with each one of them. Would be my suggestion. Specifically, I'm blinking out on what it is right now. Explore what that parentheses does. The parentheses, I believe, is going to say, look at the actual address stored there, or treat it as an address. And then when you have the 181, let me look at that. It's namely because the parentheses, that's like not unique to load effective address. That is its own thing. So the idea is that we want to figure out what that does prior to going to like load effective address. Okay, so yeah, it does treat as an address. Okay. So it's like, go ahead and load up the content. That's what my guess is. I guess says, go ahead and load up the content in there and treat that information as an address. Well, I mean, it's kind of like the pointer. Like the pointer is a value to an address. So it could be that an address is stored in RDI. At that address, yeah. Seems very... Specifically, look up the parentheses notation. That is something on its own that I can't recall off the top of my head. But look up the notation for that and feel, I would say, get comfortable with that. I wonder where it is in this book. I think it's up to 3, but oh, here it is. Found it. It's going to be on page 169. It's under 3.4.1. So that is showing the notation. So we can see that if it's $, then a number, then it's immediate. But if we're in that notation, that means we're doing a scale index where it's open parentheses, comma, some value, comma, some other value. And if we look at this, we can see that it's effectively Figure 3.3. Yeah, operand's forms. So when you look at that column of form, that's what we're actually seeing there. And so we see that we're in the memory type where we are doing the, I see it on my screen from fourth from the bottom. What do you mean the outside thing? Oh, that is going to be in the form of, yeah, is it immediate? I'm pretty sure that's in the last form. Oh, sorry, it's going to be the form right after. So it's going to be, sorry, the form without the one is going to be fourth from the bottom. The form with the one is going to be third from the bottom. It's all kind of like one argument almost. Because if you look at the operand value, you can see it's doing, it's all kind of just one big equation that utilizes everything. And that is going to be like what is load effective address is going to be using. So there's not really it translates to the operand value. It's not like it does multiple operations at once, if that makes sense. In a way it does, in a way it doesn't. It really just kind of calculates what the operand value is given that table. So that table is it's going to be an important one to kind of look at and remember. Sorry, not remember, but at least understand that on the exam, you should be able to look at that and be like, yes, I know what's going on. So whenever we're doing, let me think to myself real quick. Yeah, I would just 3.4.1 is going to be a very good chapter to kind of section to review. So when it means base and then index and code, what does it mean for each? Oh, for the name. So the scaled index is trying to show it's when it says index, it is referring to it almost like an array where it's indexing something. And when it says scaled index, it's because just like we might do with an integer array, we always skip by a factor of 4 bytes. So the scale, that's where that kind of like that scale notation comes from. I don't understand what you mean by level 2 of operand forms. It's not I wouldn't really consider it a shift. It's more like a hop. It's a jumping almost. So we have a pointer, right? And if we have an integer array A, we have a pointer to the beginning of the memory address. And when we index A at say 2, we're actually skipping ahead 8 bytes and then reading the next 4 bytes. So that's where that scaled index is because we have a number 2, and that's kind of indicating the index that we're skipping by, and our scale value would be 4. Yeah, that would be, because that's the first argument before the first item there is going to be the third from the bottom on the operand forms, and then the one on the right, R8, is going to be just the register. So that is effectively saying, go ahead and read the contents of the register, and we're going to consider the scale value be 4, and we're also going to multiply it. So yeah, we're going to multiply the value by 4 and then add 1, whatever that does. So yeah, I would. That's going to be a very good table to review, because that's going to be answering a lot of those questions. I don't feel confident enough to right now to explain, to give an example of how it would look like, but that is going to show how everything happens. Because I'm pretty sure it's saying don't get the content of that, instead get the address of it and store it. Is my guess. Okay. I need to hop off now, but I hope this was helpful to you guys. Yeah. See you guys.